At the dawn of the 20th century, the atom was still a mystery wrapped in certainty. Scientists believed it existed. They used it to explain chemical reactions and the structure of matter, yet no one had truly seen inside it. The prevailing model described the atom as a soft, uniform sphere of positive charge with tiny negatively charged electrons embedded within it, like small particles scattered through a larger mass. It was a simple and comfortable picture, one that seemed to fit the evidence available at the time. But it was wrong. The person who would break that illusion and reveal the true structure of the atom was Ernest Rutherford, a physicist whose experiments did not just refine existing ideas, but shattered them completely. Ernest Rutherford was born in 1871 in rural New Zealand, far from the major scientific centers of Europe. His early life was shaped by hard work, discipline, and a strong emphasis on education. His family valued learning, and despite limited resources, Rutherford showed remarkable ability from a young age. He was curious, energetic, and deeply determined, qualities that would later define his approach to science. Growing up in a farming environment, Rutherford developed a practical mindset. He was used to solving problems directly, observing results, and adjusting his approach based on what worked. This hands-on way of thinking would later influence how he conducted experiments, focusing not just on theory, but on clear, decisive evidence. He studied at the University of New Zealand, where his talent quickly became evident. His work in physics earned him recognition and eventually a scholarship that allowed him to travel to England. This was a significant turning point in his life. Moving from a distant colony to the center of the scientific world placed him in an environment filled with opportunity and competition. At the Cavendish Laboratory in Cambridge, Rutherford began working under J.J. Thomson, one of the leading physicists of the time and the discoverer of the electron. The laboratory was a place of intense experimentation, where new discoveries were being made about the structure of matter and the nature of electricity. Rutherford quickly distinguished himself. He began studying a newly discovered phenomenon known as radioactivity. Certain materials, such as uranium, were found to emit invisible rays that could pass through objects and affect photographic plates. These emissions were not well understood, but they suggested that atoms were not as stable or indivisible as previously thought. Rutherford approached this problem with characteristic energy. Through careful experiments, he discovered that these emissions were not all the same. He identified two distinct types, which he named alpha rays and beta rays. Alpha rays were relatively heavy and carried a positive charge, while beta rays were much lighter and carried a negative charge. Later, a third type, gamma rays, would also be identified as a form of high-energy radiation. This work was important because it showed that atoms could break apart and release energy. The idea of the atom as an indivisible unit was no longer tenable. Instead, atoms contained internal structure and could undergo transformations. This realization marked the beginning of nuclear physics, a field that would grow rapidly in the years to come. Rutherford's interest in radioactivity led him to McGill University in Canada, where he continued his research. There, he made another crucial discovery. He showed that radioactive elements change into different elements over time. This process, now known as radioactive decay, revealed that atoms are not fixed entities but can transform, releasing energy in the process. This was a profound shift in understanding. It suggested that the elements themselves, once thought to be fundamental and unchanging, could evolve into other forms. Rutherford's work was not only experimental, but also conceptual. He introduced the idea of half-life, the time it takes for half of a radioactive substance to decay. This concept allowed scientists to measure and predict the behavior of radioactive materials with precision. It also provided a tool for understanding processes that occur over long periods, including geological and cosmic timescales. Despite these achievements, Rutherford's most famous discovery was still ahead. By the time he moved to the University of Manchester, he had already established himself as a leading figure in physics. It was there that he began the series of experiments that would fundamentally change the understanding of the atom. The question he set out to answer was deceptively simple. If the atom is a uniform sphere, as widely believed, how do particles pass through it? To explore this, Rutherford and his collaborators designed an experiment using alpha particles, the heavy, positively charged emissions he had previously studied. They directed a beam of these particles at a very thin sheet of gold foil, expecting that the particles would pass through with only slight deflection, since the atom was thought to be mostly uniform and diffuse. At first, the results seemed to confirm expectations. Most of the alpha particles passed straight through the foil with little or no deflection. But then something unexpected happened. A small number of particles were deflected at large angles. And even more surprisingly, a few particles bounced almost directly backward. This result was astonishing. According to the existing model, such deflections should have been impossible. There is nothing in the atom, as it was then understood, that could produce such strong forces over such small distances. Rutherford later described this moment with a sense of disbelief, comparing it to firing a shell at a piece of tissue paper and having it bounce back. The only explanation was that the atom was not a uniform sphere. Instead, it must contain a very small, dense center where most of its mass and positive charge were concentrated. This central region, which Rutherford called the nucleus, was capable of exerting a strong force on the alpha particles, causing them to deflect sharply or even reverse direction. The rest of the atom, by contrast, was mostly empty space. This realization transformed the understanding of atomic structure. The atom was no longer a solid object, but a system with a dense core and electrons moving around it at a distance. It was a structure more like a miniature solar system than a uniform sphere. With this discovery, Rutherford had uncovered the nucleus, and in doing so, he had fundamentally changed how humanity understands the nature of matter itself. After the results of the gold foil experiment became clear, Ernest Rutherford found himself standing at the edge of a completely new understanding of matter. The atom, once imagined as a soft and uniform sphere, had revealed something far more surprising. It was mostly empty space, with a tiny, dense nucleus at its center containing nearly all of its mass and positive charge. This idea did not simply refine the existing model. It replaced it entirely. The implications were profound. If atoms were mostly empty space, then the solid world people experience every day was not solid in the way it appears. The hardness of materials, the structure of objects, and the stability of matter all had to be explained in a new way. The discovery of a nucleus raised as many questions as it answered. What held the electrons around the nucleus? Why did they not simply fall into it? What forces operated within the nucleus itself? Rutherford's nuclear model provided a clear structure, but it was not yet a complete theory. According to classical physics, electrons moving around a nucleus should continuously lose energy and spiral inward, eventually collapsing into the center. This problem, later addressed by Niels Bohr, showed that a new kind of physics was needed to fully explain atomic stability. Rutherford's work had opened the door, but others would need to walk through it. Even so, his discovery marked a turning point. It established the nucleus as the central feature of the atom and laid the foundation for all future research in atomic and nuclear physics. Scientists now had a new framework to explore, one that focused on the internal structure of the atom rather than treating it as an indivisible unit. Rutherford did not stop with the discovery of the nucleus. He turned his attention to understanding what the nucleus itself was made of. Through further experiments, he showed that the nucleus contains positively charged particles, which would later be called protons. These particles accounted for the positive charge that deflected the alpha particles in the gold foil experiment. At the time, however, the full composition of the nucleus was not yet known. The existence of neutrons, particles with no electric charge, would only be discovered later by James Chadwick, one of Rutherford's own students. This discovery helped explain how nuclei could contain multiple particles without being torn apart by the repulsion between positively charged protons. Rutherford's influence extended far beyond his own experiments. He was known as a powerful and energetic leader in the laboratory, guiding students and collaborators with a direct and practical approach. Unlike some scientists who preferred quiet reflection, Rutherford was active, decisive, and often enthusiastic in his work. He encouraged experimentation, valued clear results, and pushed those around him to pursue bold ideas. Many of the most important figures in early 20th century physics worked under his guidance. In this sense, Rutherford was not only a discoverer, but also a builder of scientific communities. His laboratories became centers of innovation, where new ideas were tested and new discoveries were made. The work done under his direction helped shape the course of modern physics. One of his most significant achievements after discovering the nucleus was the first artificial transmutation of an element. In 1917, Rutherford conducted an experiment in which he bombarded nitrogen gas with alpha particles. During this process, he observed that the nitrogen atoms were transformed into a different element, oxygen. This was the first time a human had deliberately changed one element into another. The importance of this moment cannot be overstated. For centuries, the idea of transforming elements had been associated with alchemy, often dismissed as impossible or purely symbolic. Rutherford showed that such transformations were real and could be achieved through scientific methods. This marked the beginning of nuclear reactions as an area of study, opening the path toward understanding how elements are formed and changed. It also hinted at the enormous energy contained within the nucleus. Although Rutherford himself did not pursue the development of nuclear energy as a practical technology, his work made it clear that the nucleus was a source of immense power. Later scientists would build on this knowledge, leading to both the development of nuclear energy and the creation of nuclear weapons. As Rutherford's career progressed, he returned to the Cavendish Laboratory in Cambridge, this time as its director. In this role, he continued to lead groundbreaking research while mentoring a new generation of physicists. Under his leadership, the laboratory remained at the forefront of scientific discovery. His approach to science remained consistent. He valued simplicity, clarity, and direct evidence. He was less concerned with abstract mathematical descriptions and more focused on what could be observed and measured. This practical mindset complemented the more theoretical approaches of scientists like Maxwell and Bohr, creating a balance that advanced the field as a whole. Rutherford's work reshaped the understanding of matter at its most fundamental level. By revealing the existence of the nucleus, he transformed the atom from a vague concept into a structured system. By demonstrating that elements could change, he showed that matter itself is dynamic rather than fixed. And by exploring the forces within the nucleus, he opened a field of study that would become central to both science and technology. The atom, once thought to be simple, had become a complex and powerful system. And through Rutherford's work, the path toward understanding that system had been firmly established. As Ernest Rutherford continued his work in the years following the discovery of the atomic nucleus, the focus of physics began to shift more deeply toward the inner structure of matter. What had once been considered the smallest unit of existence was now revealed to be a complex system, and Rutherford stood at the center of this transformation. His earlier discoveries had broken the old model of the atom, but now a more difficult task remained. It was no longer enough to show that the atom had a nucleus. The challenge was to understand what that nucleus was made of, how it held together, and what forces operated within it. The nucleus presented a puzzle that was both simple and deeply complex. On one hand, Rutherford had shown that it carried a positive charge and contained most of the atom's mass. On the other hand, this raised an immediate question. If the nucleus contained multiple positively charged particles, why did they not repel each other and fly apart? According to the known laws of electricity, like charges repel strongly, especially at very small distances. Yet atomic nuclei were stable, holding together despite this repulsion. This suggested that a new kind of force must exist. Although Rutherford himself did not fully identify this force, his work made it clear that something beyond classical electromagnetism was at play within the nucleus. Later, this would be understood as the strong nuclear force, one of the fundamental forces of nature. But during Rutherford's time, the idea of such a force was only beginning to emerge from experimental hints and theoretical necessity. Rutherford's approach to these problems remained grounded in experimentation. He was not primarily a mathematician or a theorist in the abstract sense. Instead, he relied on carefully designed experiments to reveal the structure of reality. His laboratory became a place where physical evidence guided understanding, where particles were directed, observed, and measured to uncover hidden truths. One of the most important developments during this period was his work on identifying the basic components of the nucleus. Through a series of experiments, Rutherford came to the conclusion that the hydrogen nucleus, the simplest of all atomic nuclei, was a fundamental building block. He proposed that this particle, carrying a positive charge, was present in all other nuclei. This particle would later be named the proton, becoming recognized as one of the core components of matter. This idea helped bring order to the growing complexity of atomic science. If all nuclei were built from protons, then the differences between elements could be understood in terms of how many of these particles they contained. This concept aligned with the emerging understanding of atomic number, which describes the number of protons in an atom's nucleus and determines its identity as a particular element. Yet even this was not the full story. Scientists soon realized that the mass of nuclei could not be explained by protons alone. There had to be additional particles present, ones that carried mass but no electric charge. This mystery would eventually be solved by James Chadwick in 1932 with the discovery of the neutron. But the groundwork for this discovery was laid within Rutherford's laboratory and through the questions his work had raised. Rutherford's influence during this time extended far beyond his own research. He became known as a central figure in the development of modern physics, not only because of his discoveries, but because of his ability to guide and inspire others. His laboratory at the Cavendish became one of the most important centers for experimental physics in the world. Young scientists came there to learn, to experiment, and to contribute to a rapidly advancing field. Among those who worked under his direction were individuals who would go on to make major discoveries of their own. James Chadwick, who would discover the neutron, was one of his students. Others contributed to the understanding of atomic structure, radiation, and nuclear reactions. In this way, Rutherford's legacy was not limited to his own achievements. It extended through the work of those he trained and influenced, shaping the direction of science for decades. His personality played an important role in this environment. Rutherford was known for his energy, directness, and confidence. He approached problems with a sense of determination, often pushing experiments forward with a practical mindset. He valued clear results over complex speculation and encouraged those around him to focus on what could be demonstrated through evidence. At the same time, he was capable of recognizing the importance of new ideas. Although his own approach was experimental, he understood that the emerging field of quantum theory was essential for explaining atomic behavior. His work provided the foundation upon which theorists like Niels Bohr could build, creating models that explained how electrons behaved around the nucleus. In this way, Rutherford's discoveries and the development of quantum mechanics became closely connected, each supporting the other. As research continued, the understanding of nuclear processes began to expand. Scientists explored how particles could be used to probe the nucleus, how energy could be released through nuclear reactions, and how elements could be transformed under controlled conditions. These studies revealed that the nucleus was not only a center of mass, but also a source of immense energy. The realization of this energy would later have profound consequences. While Rutherford himself viewed the extraction of nuclear energy as unlikely to become practical, the discoveries made in his field would eventually lead to developments that changed the world. Nuclear reactions would become both a source of power and a source of destruction, highlighting the dual nature of scientific progress. Through all of this, Rutherford remained focused on the pursuit of understanding. He continued to lead research, mentor scientists, and contribute to the growing body of knowledge about the atom. His work had transformed the way matter was understood, revealing that beneath the surface of ordinary objects lies a complex and dynamic structure governed by forces that were only beginning to be explored. The atom was no longer an abstract idea. It had become a detailed system, with a nucleus at its center and particles interacting in ways that define the nature of the physical world. And at the heart of this transformation was Ernest Rutherford, whose experiments had opened the door to the hidden structure of reality. As Ernest Rutherford moved into the later years of his life, the full weight of his contributions to science had already begun to reshape the modern understanding of matter. The atom, once imagined as a simple and indivisible unit, had been revealed through his work to be a structured system with a dense nucleus at its core. This discovery alone would have secured his place in history, but the broader impact of his work extended far beyond a single breakthrough. He had not only uncovered a new model of the atom, but had also opened an entirely new field of study, one that would influence physics, chemistry, and technology for generations. By the time Rutherford returned to Cambridge as the head of the Cavendish Laboratory, he was no longer just an experimental physicist making discoveries. He had become a central figure in the scientific world, guiding research and shaping the direction of future investigations. The Cavendish Laboratory, already known for its contributions under earlier leadership, became under Rutherford a place of intense activity and discovery, where the structure of the atom and the nature of the nucleus were explored with increasing depth. His leadership style was direct and grounded. Rutherford believed in clear, decisive experiments. He valued results that could be observed and verified, often encouraging his students to focus on simple but powerful methods rather than overly complicated approaches. There was a sense of energy in his laboratory, a forward movement driven by curiosity and determination. Scientists working under him were not only learning techniques, but also absorbing a way of thinking, one that emphasized evidence, persistence, and clarity. During this period, some of the most important discoveries in nuclear physics emerged. In 1932, James Chadwick, working within Rutherford's circle, discovered the neutron. This particle, with no electric charge but significant mass, provided the missing piece in the understanding of the nucleus. It explained how nuclei could contain multiple protons without being torn apart by electrical repulsion. The presence of neutrons allowed for a stable structure, held together by forces that operated at very small distances. This discovery completed, in a fundamental way, the picture that Rutherford had begun. The nucleus was no longer just a dense center of positive charge. It was a complex system made up of protons and neutrons, interacting through forces that were only beginning to be understood. This deeper understanding opened new possibilities for studying nuclear reactions, as scientists now had a clearer idea of what they were dealing with at the smallest scales. Rutherford's earlier work on transmutation also took on new meaning in this context. The idea that one element could be transformed into another was no longer an isolated observation, but part of a broader understanding of nuclear processes. Scientists began exploring how nuclei could be altered, split, or combined, leading to reactions that released large amounts of energy. Although Rutherford himself remained cautious about the practical use of such energy, the path had already been set. Beyond the laboratory, the influence of Rutherford's discoveries continued to expand. The understanding of atomic structure became essential to chemistry, explaining how elements combine and interact. It influenced materials science, shaping the development of new substances with specific properties. It also laid the groundwork for technologies that would emerge later, including nuclear energy and various forms of radiation-based applications in medicine. Yet alongside these advancements came more complex consequences. The same knowledge that allowed scientists to understand the nucleus also made it possible to release its energy in powerful and potentially destructive ways. While Rutherford did not directly participate in the later development of nuclear weapons, his work formed part of the scientific foundation that made such developments possible. This dual aspect of scientific progress, where knowledge can lead to both creation and destruction, became one of the defining features of the 20th century. Despite these far-reaching implications, Rutherford himself remained focused on the pursuit of knowledge. He was known for his straightforward personality his strong presence in the laboratory, and his ability to communicate ideas with clarity. He did not present his work in overly complex terms, but instead emphasized the physical meaning behind the results. This approach made his discoveries not only significant, but also accessible to those willing to engage with them. He received numerous honors for his work, including the Nobel Prize in Chemistry in 1908 for his investigations into the disintegration of elements and the chemistry of radioactive substances. This recognition reflected the broad impact of his research, which crossed the boundaries between physics and chemistry, showing how deeply interconnected these fields had become. Rutherford died in 1937, leaving behind a transformed scientific landscape. By the time of his death, the atom was no longer a mystery in the way it had been at the start of his career. Its structure had been revealed, its components identified, and its behavior increasingly understood. The questions that remained were now more detailed, more precise, and built upon the foundation he had established. His legacy is both clear and far-reaching. He is often called the father of nuclear physics, a title that reflects not only his discoveries, but also his role in shaping an entire field of study. The nucleus, once hidden and unknown, became through his work the central focus of scientific exploration. From this understanding grew technologies and theories that continue to influence the modern world. The impact of Rutherford's work can be seen in many areas of life today, from the generation of energy in nuclear reactors to the use of radiation in medical imaging and treatment. The principles he helped uncover remain active and relevant. Even in fields that seem far removed from physics, the understanding of atomic structure plays a crucial role, influencing everything from materials to biology. Looking back, Rutherford's journey reveals a pattern that appears throughout the history of science. A simple question leads to an experiment. An unexpected result challenges existing beliefs. A new idea emerges, reshaping understanding and opening further questions. In Rutherford's case, this process led to the discovery of the nucleus and the transformation of atomic theory. What began as an attempt to understand how particles pass through a thin sheet of gold became a gateway into the hidden structure of matter itself. Through careful experimentation, persistence, and a willingness to question established ideas, Ernest Rutherford revealed that beneath the visible world lies a complex and dynamic system, one that continues to shape the way we understand reality at its most fundamental level.